Well, thank you everyone for joining today. This is the Future Frontiers, How AI Will Shape the Next Decade of Semiconductor Packaging. My name is Brittany Holmes. I'm an Associate Director with ASU's Ira A. Fulton Schools of Engineering, Office of Global Outreach and Extended Education, or GOE. GOE brings this vast experience of ASU engineering faculty, enabling engineering degree programs online, professional programs, custom programs, and also supports capacity building projects around the globe. Today's session is part of the ASU Engineering Professional Development Series. Our goal is to connect all of you, whether students, faculty, current professionals, alumni, with engaging professional development opportunities. And today we're going to start with some brief polls just to get to know who's in the room. We'll have two 20-minute presentations by our esteemed faculty, and we'll also have time for some questions at the end. Feel free to enter any of your questions into the Q&A throughout the session, add any comments into the chat feature, and attendees are all muted, but we hope you'll engage with us through the Q&A in the chat. We do want to hear from you. So before we launch into presentations, if you would take a moment, we're going to pull up some brief polls just to get to know you, who's in the room. Let's see, I think Nikki's going to pull up.
Yeah, correct. I need to pull up the poll. Go launch.
So first is what best describes your background, just getting to know where you're coming in from today, and then what is interesting you most in AI and packaging? So what's kind of driving your interest in this area? We'll give you a minute to just go ahead and click on those. Awesome. And do you want to close that poll, and are we able to see those responses here?
Yes, here we go.
So look, okay, it looks like we have some ASU students, quite a bit of faculty and staff, primarily folks from industry, so welcome, and also a few recent grads and alumni, and really interest across the board, whether career, industry trends, general curiosity. So we appreciate you joining. Thanks for jumping in with us today. Well, now I'm going to go ahead and introduce our panelists, or our presenters. So it's exciting to have these two on with us today. They have a wealth of experience. I'm grateful to have been able to work with both of them on programs supporting the development of the semiconductor workforce. So first, Dr. Hongbin Yu is a professor at Arizona State University. He's the director of the NSF IUCRC Center for Efficient Vehicles and Sustainable Transportation Systems. He holds a PhD in physics from the University of Texas at Austin and is a member of the Executive Council of the International Microelectronics Assembly and Packaging Society. Professor Yu is an expert in nanotechnology, flexible electronics, and automotive semiconductor applications, leading research that advances sustainable transportation and innovative semiconductor technologies. Dr. Christopher Bailey is a professor at Arizona State University and director of the Center for Advanced Semiconductor Packaging. He leads cutting-edge research in thermomechanical modeling and reliability of semiconductor packaging, with significant funding from the U.S. CHIPS Act projects. Previously, he served as the Associate Dean for Research at the University of Greenwich in the UK and has published over 400 papers in the field. Professor Bailey is a recognized leader in electronics packaging. He's received many prestigious awards, including the IEEE Electronics Packaging Society David Feldman Award, and actively serves on several IEEE boards and editorial roles. So with that, I will hand it over to Professor Yu.
All right, thanks, Brittany, Nikki. Good morning, everyone, or well, good afternoon, wherever you are. Yeah, so as Nikki and Brittany mentioned, yes, we are trying to use this opportunity to connect, to introduce AI, in particular related to packaging. So they're going to, Professor Chris Bailey, we're going to have a two different aspect, right? One is, I'll first talk about the packaging using AIs, right? Yeah, we heard a lot of AI these days. And then Professor Chris Bailey will talk about, yeah, how the AI can in turn help the packaging side. So let's get started. So I'll talk about segment of packaging powering AI applications. Next slide, please. Yeah, so probably almost every year, one of you probably noticed or heard of AI the last couple of days, especially large language model, ChatGPT 3, ChatGPT 4, and a few days ago, ChatGPT 5. So these actually summarize, I think, in a way you already experienced, whether you're doing Google search, you notice actually compared to a few years ago, you got a random lot of unrelated result. Now they give you a summary, a lot more focused and probably more precise on target. And also probably use the Microsoft, you see some Copilot AI and so on and so forth. But some of the probably in the industry might specifically use AI tools tailored for different applications. So these actually are enabled by the so-called large language model. So what this slide shows evolution of this AI models, right? From on the left to in 1998 to 2011, 2012, AlexNet, which is ImageNet, and then now ChatGPT 3, 4 years ago to now ChatGPT 4, and now just a few days ago, probably ChatGPT 5. What I want you to focus on actually in terms of training data, right? All this AI, ML, they're basically using a program that train using data set to train their model, right? Then you recognize to generate some certain pattern. And then the second step, then people then can use this trained model, right, for application to recognize images or recognize objects in the large language model, generate a text, right? Or even entire article of your interest, right? So if you look at the training data set, looking at the AlexNet 2012, it has 1.2 million training examples. So on the next slide, I'm going to show you some other data we use. But if you look at, not yet, but if you look at ChatGPT, so now there is significant of a step up, right? It's 500 billion training tokens, right? ChatGPT 13 trillion. And then accompany that the training compute, right? The compute requirement. So AlexNet has a 3 trillion flops, right? That basically, and then for ChatGPT, you have a 1 plus exaflops. One exo is 1 to the power of 18, right? There is 18 zeros after 1, right? So significant increase in that. And also, if you look at the parameters, right, 60 million parameters for the AlexNet, and there's 175 billion parameters for ChatGPT, 96 layers, right? So significant kind of increase in number of parameters. Next slide, please. So just to tie to, for instance, yeah, there is some work in my lab. Yeah, Brittany mentioned that background. Yeah, so I have a center. We look at some of the application using the LiDAR image camera to look at for transportation application. Then using this similar like ImageNet kind of a trained neural network to recognize cars and LiDAR objects. Right, so these are early days, or a few years ago, still using this. This is still being used. But now, if you look at the ChatGPT, right, the nowadays AI. Next slide, please. Yeah, so as the first slide showed, actually significant more training parameters, right? So here's what's the sort of a training process look like, right? So you have a matrix calculation, right? So use some input, multiply some weight, right, plus some kind of a bias. And that's what generally a training look like, the neural network. But the key is actually for the GPT, large language model, and others, right? Sort of XAI, those models, they have a significant more inputs, right? And then many more matrix calculation. Just summarize again, right? ChatGPT 3, right? Using has 175 billion, right? Those parameters you need to as input, right? So ChatGPT for 1.4 trillion. Right, so therefore, a lot of really the data center these days require this really matrix calculation. Next slide, please. Yeah. So here's the sort of the summarize this in a different graph, right? So on the horizontal axis, release date or the year timeline. The vertical axis, AI and this model size, right? Evolution in terms of parameters, training parameters, right? On the light blue shows actually what the memory used in training, right? NVIDIA early days up to recent years, 2022, NVIDIA H100. Of course, there's also the B200 now, Blackwell. So that's 80 gigabytes kind of a memory and that steady increase. While the demand, right, the purple line, right, ChatGPT 3 and 4 significantly require more input, right? So for the like I said earlier, needed input there. So therefore, there is a so-called memory wall, right? It's compute is one thing, but need a lot more memory to shuffle the data between memories. Yeah, so that's the intermediate step. So next slide. Please. Yeah. So therefore, they require a very different data center or computation sort of architecture to support this large language model, the recent AIs, right? So therefore, there's some matrix for AI for packaging, right? How do you tie these together? So I mentioned there is a need to increase the number of memories, right? Need a large bandwidth of memory. So the data throughput between processors memory need to shuffle data between the processor and memory constantly, right? So need a great I/O and interconnects. And also need to reduce latency. What does it mean? Actually need to take a short amount of time to send data between different these processors, right? Between processors and memory as fast as possible. So therefore, one of the ways to, of course, to get the shorter interconnect. If you remember the PC, right? The typical PC, you have a CPU, right? You have a slot for CPU card, and you have a separate DRAM, right? Memory card. So the communication is really through the motherboard. But if you look at these days, I'm showing the example. So now this to shorten the interconnect, you have to go through the packaging. We are not going to go to the PCB directly, right? So you have to shuffle the data through advanced packaging, right? So that's critical in terms for the data for quickly getting data between the processors, and also reduce energy to transfer data. So therefore, energy required to transfer data using picojoule per bit. It characterizes that, and need to reduce energy loss, and also need for shorter interconnect. You probably heard these days, a data center require a lot of energies, right? So for instance, your data center these days require easily megawatts energy, even tens of megawatts. So therefore, they're even trying to build a data center using near the nuclear power plant, right? Just the sheer amount of energy needed. And also because it generate a lot of heat, using a lot of energy, right? Shuffle a lot of data quickly. So you generate a lot of heat, therefore need a better thermal management and solutions, and therefore the reliability, right? Under those heat, right? The packages has to be really taken into account. Need to reduce power losses and remove heat as much as possible. All right, next slide, please. Yeah, so here is how exactly the AI data center been made. So let's starting from the module. This is a few years ago, the NVIDIA H100. Yeah, this is the module that probably give you the size on the right side compared to a palm. The back side of this module. On the top, at the center, you see a package, yeah, on the H100, the dies and GPUs together. And then I also want to point out, yeah, so actually silicon chip is only the center, the square one. But actually, to support that, you see a lot of other black stuff on the left and the right. So therefore, a lot of power management, right, and some of the passives in there. So therefore, one of the key things also trying to minimize those support units as much as possible. Next slide, please. So take a closer look, right? So this is the same H100 module, right? So how these things put together, right? On the right is a little bit closer up of the center square. So now you can see in the center of this is the H100 GPU die. This is actually one die. And the surrounding, there's three dies on each side, right? They call it HBM, high bandwidth memory. So overall, there are total 80 gigabytes memory That's on the plot I showed earlier. For H100, there are 80 gigabytes memory accompany each of these GPU dies, right? Just constantly imagine shuffling between the data between HBM and GPUs, right? Because it's a matrix calculation, you need to store those matrix element after computation and for the next round of calculation there. So now if you take the next slide, please. If you take a slide, yeah, next, yeah. If you take or go backwards one. Yeah. So, yeah, stop here. So if you take the cross section, right, like the red line indicated, and look at a cross section here, right? So here you can see, so now, yeah, so you have a center, the SoC, in this case, the GPU, NVIDIA GPU, and then you have a stack of HBM, right, at high bandwidth memory. This is actually not just the HBM is not just one die, as the cartoon indicated, actually several dies together, right? We call this 3D stacks, right? You have a silicon stacking another silicon die. But between the SoC and HBM, you see actually they have to connect, right? Like I mentioned, you need to constantly shuffle a large amount of data between HBM and SoC. So therefore, they use the smaller pitch dies, right? Connecting shuffling data between HBM and silicon interposer. And then there's sort of a substrate, right? The bottom part is called a substrate, and mounted a substrate eventually will go to a PCB board. So therefore, the data, so we'll not be going through the motherboard, the PCB board, like the traditional the PCs, right? So here, because that lens is too long, right? Large latency wastes a lot of energy. So here you need to shuffle between HBM and SoC. And also want to point out, so actually these dies look on the right, the physical picture there looks similar, but actually come out a different foundry or different semiconductor manufacturing facility. For instance, the NVIDIA GPU is made by TSMC, right? And HBM is typically those high bandwidth memory made by others, right? For instance, Micron could be SK Hynix, right? So therefore, you need a packaging technology putting these dies from different foundries together. So really, advanced packaging play a critical role here. Next slide, please. So just now giving you a little bit of a flavor, but how exactly they put this together? Again, I mentioned this compared to sort of a traditional data center, which heavily based on the CPU. But now these days, for the AI training and the inference, they use more GPU-based the data center, right? The hyperscaler that they typically used to call them, or because you need to do the matrix calculation. So now on the top left, is a number of these H100 modules, right? A number of those, right? You see probably is eight of those. And now on a little bit top right, so now this, after you put some thermal solutions, heat sink, right? As I mentioned, they generate a lot of heat. So put solutions there and then put it into a box, right? And then that one box, one box and then put in the rack, and then you have several racks, right? That's how the data center these days being put together. Of course, you need a very fast data communication between the dies, right? Between the modules, right? Between the racks, or between those even different row of racks in there. So therefore, high-speed communication is very important. Next slide, please. All right. So now here's the most recent one. I think this is the NVIDIA Blackwell. So this is one, if the one here on the circle, you might be able to see on there actually the two rows, right? One on the left, one on the right. So each side have a 4 HBMs, right? In the center is the newer GPU. That actually GPU has 2 GPU dies, right? Connect to use high speed link together, right? So to create almost serve as a single die. So that's what the new Blackwell hardware look like. And then you can see this actually also have 2 dies together compared to H100. You have just one sort of a module. And then the one on the bottom actually just provide a link, high speed link between these 2 modules here. So really the communication between those is very important. So not just NVIDIA is making the AI, the data centers. Of course, AMD is also making GPUs and CPUs. They're also trying to get into this area. So one of the product that AMD push out, is called the MI series. They're looking at MI300. I think they're also putting a MI350 out this year, and next year it's going to be 400. As you can see, this cartoon, there are already several layers there, right? Can you go to the next slide, please? So these actually give you, this taking AMD's Instinct, the MI300 family, they call the 3.5D advanced packaging because they involve the 2.5D, if you look at the in the middle here, but also 3D hybrid bonding. So therefore, the stacking compared to NVIDIA I just showed earlier, so it's significantly more complex, right? Rather than just HBM and GPU tied together with silicon interposer. And now this one has a three different 3D structure and silicon die, the XCD on ICD, then and connect together. And then on the right side is actually the cross-section SCM image, just shows you how complex, right, of this structure is, and the various soldables at the bottom close to the substrate, right, and then there is micro bumps, and then the one you cannot see using 3D hybrid bonding. So therefore, for those complex structure, you need a very advanced bonding technique called a 3D hybrid bonding, to tie this together. Next slide, please. Yeah. So who is doing this, right? So both NVIDIA, AMD, they call it fabless, right? They're designing these chips, right? Whether it's the H100 or others, the MI300. So as I mentioned, yes, TSMC is a key player, right? So they're here. So the package technology 2.5, called the CoWoS, chip on wafer on substrate, that they used in the both NVIDIA and MI300 use that. But on top of that, there's a 3D IC on the top right corner there. So 3D packaging allow people to put really complex dies together, right? So at ASU, we're also establishing some capabilities there. Next slide, please. All right. So what's the future? Yes, hopefully I give you a flavor on the kind of a breakup and analysis of what the packaging technology used in these days data centers, right, for the AI training and inference. So future packaging is you see center here. So a lot more complex. Not only you have a multiple 3D connected front end dies, and also there is especially they call the high speed standard die to die interface or UCIe. On the top right, you're gonna see of course still have a memory, have a compute dies, right? It's another player actually people may have heard called Broadcom. They're now using GPU. They have ASIC, right? Application specific ICs to accelerators, right? So because GPU is more general purpose, right? And actually used for the specific purpose, application specific. And now here is also see this co-package optics here. Next slide, please. Yeah. And they just kind of highlight that's NVIDIA's vision. Yeah, so they're moving the photonics side, right? So photons much faster. Right now, initially was outside of a package, right? But now to move on to a closer as much as possible. The silicon photonics, if you see the little green die here, called of photonic IC, put on the same substrate as the switch ASICs, right? To put the photonics into the electronic integrated circuits here. That's the trend in order to increase the speed. Next slide, please. All right. I've talked about a lot of data centers, so for the high performance computing side, but that's for sure, there's high value, right? High value kind of AI training and inference. But in terms of sheer numbers, there are not that many, even though actually they're building a data center using 100,000, for instance, H100 by XAI, but actually a lot more edge AIs, right? So devices, for instance, using the industrial application, autonomous vehicle, IoT, so on and so forth. So in addition to the requirement I mentioned earlier for the edge, for the general AI training, for AI packaging, but here for edge AI, still need a high speed, But here definitely need a compact size, lightweight in many cases, and the power efficiency, right? Because it's on edge, right? It cannot have a nuclear power supply, power plant to supply that edge device, and also robust thermal solutions, thermal management. Typically, they require lower costs, so therefore lead to efficient. It's also involve advanced packaging, including 2.5 and 2.5D and 3D integration there. So there will be, but of course, the cost cannot be too high for many of these applications. But there are a lot more devices using Edge AI. Next slide, please. All right. So here is just quickly a summary. Yeah. So all this actually, we are doing this. Professor Chris Bailey and many of our colleagues at ASU. We are not just kind of studying this, teaching this, but we are actually have the funding and the infrastructure to do this, right? So it's a part of the CHIPS Act, as Bernie introduced. Professor Chris Bailey, ASU has received significant CHIPS Act funding to support the packaging side. Next slide, please. So one effort is called a Swap Hub. We have ASU located ASU Research Park. So one of the key capabilities we're building is we call the hidden integration, which is to use a Decker's fan-out wafer level packaging to create a 2.5D, 2D, 2.5D, and 3D integration. Next slide, please. So the other big effort is from Department of Commerce, right? From NIST support, managed by NIST, is to AIC work with DECA to we call it Shield USA advanced substrate. As I mentioned, NVIDIA, the H100, they need advanced substrate in order to accommodate high density interconnect. So ASU will be building advanced substrate to support AI application among other applications. So that's basically what the packaging's been used in AI. But now Professor Chris Bailey, next slide please, will be talking about the other way around. So how AI can help advanced packaging. Yeah, Chris.
Great, thank you very much, Hongbin. Am I coming through loud and clear, Hongbin?
Yes, very clear.
Okay, well, thank you. So yes, now we heard Hongbin talk about the need for advanced packaging, particularly for these AI applications. And remember the memory wall Hongbin was talking about, and the need to bring die much closer together, the memory, the processors, much closer together to address that memory wall. So that's really looking at packaging for AI. But how could we use AI and machine learning algorithms to help generate the next generation of package architectures to address things like the memory wall? So I'm going to go through some of the sort of things that are happening today, because we have been and we are generating huge amounts of data. So the opportunity is here, and it's happening today, and it's evolving, is how can we use machine learning algorithms and AI techniques in design, in tests. And I'll say one word here, or two words, digital twins. We're seeing significant interest in what we call digital twins, which will be based on AI type techniques and machine learning to support the packaging engineer as we go forward when they're looking at EDA, modeling, and tests. Next slide, please. Okay, so as Hongbin was highlighting, and just to come back to this slide you would have seen earlier, because it is incredibly important for driving packaging innovations. And so bandwidth, latency, minimizing energy dissipated, and also thinking about reliability of these very complex packages. So these are some of the metrics that drives us forward, but how, as well as addressing these metrics in real packages, how can AI and machine learning help us achieve this? Next slide, please. Okay, so in electronic design automation, companies such as Cadence, Synopsys, Siemens, are certainly looking very carefully at these AI and machine learning techniques. And here in design automation, it's about how we connect and how we place die and how we connect them together through some very complex routing. So in terms of physical design there's a lot of optimization taking place, and also the trade-offs that we have to look at when we're thinking about electrical, thermal, and mechanical constraints. So these can be very complex, time-consuming optimizations taking place here in EDA software. But huge amounts of data can be generated through these tools. But also, how can AI and machine learning algorithms help us address some of these challenges much more effectively and more quickly based on a lot of data we may have generated in the past? Next slide, please. So when we think about the modeling side of things, we are now seeing a lot more integration with some of the tools when we think about signal and power integrity, temperatures, and stress that leads on to reliability concerns. But the traditional tools today, just like the traditional EDA tools today, are complex. We are moving towards multi-physics type analysis. But some of these tools based on finite element techniques are very, very time consuming. So can we use AI machine learning techniques in the future to do much more, the calculations much more quickly? And that would help what we call design space exploration in looking at new materials, new ways of doing the packaging. Next slide, please. And so I talked about the sort of things we're doing today and the trends going forward in EDA, the trends going forward in modeling and simulation, much more towards what we call multi-physics today and multi-scale calculations, very complex, but also tests. So we have our traditional tests at package level and at board level. These can be very time consuming, very expensive. We will do it. It needs to be done to qualify packages, and there's all the failure analysis that will go with this. But generating lots of data here. And the opportunities in the future is, well, how can I interface machine learning techniques into this test flow to ensure that we can do the test much more quickly, avoid the high energy costs, and in particular, avoid retesting, which is very time consuming, very expensive, and some of these tests are very energy consuming. Next slide, please. Okay, well, that really is sort of a summary of some of the things we're interested here in the EDA side of things, routing, floor planning, die placement in the package, the modeling and simulation that supports that, the move today towards multi-physics and multi-scale, because there's a lot more interaction now with the physics, particularly at high frequencies. And think about the close placement of these die and some of the thermal issues we may have there, as well as thermomechanical. So opportunities for AI and machine learning. It is AI for EDA. It is AI for modeling. It's also AI and machine learning integrating with each of the packaging processes that we have for advanced packaging. And that starts bringing in digital twins that we're seeing a lot of interest today. And then AI for tests. So how can we use a lot of the data that is being generated here? And data is really important. So huge amounts of data being generated. How can we use that data with some of these machine learning and AI techniques to generate knowledge, but also help minimize the cost of test, help ensure we get the packaging architecture and the packaging processes right first time, minimize the amount of time required for modeling, and also effectively do all the optimization in EDA again right first time. Next slide, please. So when we think about some of these AI machine learning methods, I just wanted to highlight here how important data is. And data is used to train these models. And you heard Hong Bin talk a little bit about neural networks and some of the training that takes place there. But the quality of the data, the sort of format for the data we have leads us to use different types of models. And here I've listed a few of these: supervised, unsupervised learning, reinforcement learning, and deep learning. So these are the techniques that we're building on here. It's how we gather the data and use that data to enable learning for these models, and then using those in a predictive way to optimize the whole packaging process. Next slide, please. So gathering the data, I won't go through all the text here, but essentially it is gathering the data. That could either be through the EDA tools and data you've gathered using these EDA tools, running finite element calculations for modeling, and you could do what we call a designer simulation approach there, which is similar to design of experiments, but you gather the data. If you're using finite element model, we call it synthetic data, and then you can train your machine learning algorithms on that data, and then the validated machine learning algorithms could repeat what a full finite element calculation, which would take much more time to undertake, but it repeats what that could do in a much more effective way. And then gathering all this test data, different failures, understanding how these failures are related to environmental conditions, temperature, humidity. But then the example at the bottom of this slide here is an image, and you can basically use a lot of the data from that image to really effectively go through machine learning algorithms to identify where defects are very quickly. So data. Data is very important for these techniques, and it's gathering that data for the training of these machine learning techniques. Next slide, please. Just some examples here of what we call synthetic data. So understanding the physics in our processes, and then using high fidelity, what we call high fidelity type models like these to understand thermomechanical, die bonding, wall pitch, metal migration. And you can see, these calculations could be what we call very multi-physics. But it's gathering the data from these calculations or real-world experiments, then using that data to build our machine learning AI type models, which we can then use for much faster design space exploration in terms of packaging for AI. Next slide, please. Okay, now I talked a bit here about the packaging process itself and using EDA tools to design these packages and do the optimization for layout and routing. I talked about how we could use AI for modeling and simulation, thermal, mechanical, electrical, and then also using AI and machine learning algorithms for test data. But of course, AI and machine learning or AI techniques can also be used to train the workforce. So if we start thinking about how technicians can use these AI techniques of augmented reality, for example, and as different types of digital twins is what we're moving on to now. These types of digital twins, a descriptive twin, information twin, we're seeing a lot more of this in the industry to support engineers and technicians. Predictive autonomous twins is really where we're going now in terms of the EDA, the modeling and simulation, analyzing test data. Next slide, please. So if we think about digital twin technologies, the key thing you can see in the image in the top right here is you have your physical objects. Your physical object could be your advanced semiconductor package. It could be your lithography machine, molding machine in the packaging process. And the data, or that's the data that you're gathering, say, from a packaging machine through sensors and other ways of gathering data, or as I mentioned before, through simulations. Then we develop the virtual model. Now, the virtual model here is primarily going to be a machine learning model. It is meant to run fast, and that is the idea of a digital twin. It is this two-way communication between what we call the virtual twin and the physical twin, or the physical object itself and the virtual model. And the idea there is this two-way interaction between the two is meant to optimize process performance. It could be used to look at prognostics and health management of assets. But in many times, the whole idea of digital twins is fast data communication between the physical object and the virtual representation of that physical object. So this is a very big area of research today here in the United States. There is what's called Smart USA, which is really supporting the development of digital twins for semiconductor manufacturing processes, as well as advanced semiconductor packaging. And AI and machine learning is playing a key role in that in terms of virtual model development. Next slide, please. Okay, so some of the benefits of digital twins. I talked about different types of digital twins where AI and machine learning techniques can be used. But if we think about the workforce that we require going forward, superb technologies to support learning. And I talked a little bit before about augmented reality and virtual reality that could do that, could be used for that. Can be used for remote operation of facilities. And what I was talking before with the EDA, the modeling, the test, it's really monitoring and undertaking what we would call what-if planning in looking at these packages for AI applications. Next slide. Great. Well, thank you very much. I take it over to you now, Nikki or Brittany.
So, Belly and Professor Yu, this is a very informative section. I'm going to launch the last poll. Thank you for all the input. It's interesting to see all the different option that sounds most exciting to use. Okay, now we enter the Q&A sections. Please use our chat or the Q&A function for questions.
Yeah, so probably while we're waiting for more questions, probably Chris and I, we can chat a little bit more, right? So Chris, I think you mentioned, yeah, all this, the AI and machine learning can be used for packaging. So what do you see the bottleneck, right? What's the challenging part that to do all this to you apply AI ML in packaging?
Yeah, the challenging part is ensuring we get good training of these algorithms and the interface between the algorithms and the particularly with digital twins, it's that interface, it's capturing the physics accurately and then having models that would run in real time and interface effectively with whatever the physical object is. So it is capturing the physics accurately in these models and then interfacing effectively. Many times we require this in real time. So those are the big areas that we're looking at for research.
Yeah, so when you talk about training, I guess there are two sources for training data, right? As I mentioned in the opening slides, I guess, yeah, initially training, right? It's a labeling data, right? The data come from, but now later on, people can generate data, right? Because just at least from my experience with automotive, the training data, or Google self-driving cars, yeah, so they may not generate enough data, yeah, so they generate kind of a 10 times or 1,000-fold more. I guess, do you see this, the real physical training data as well as generated data?
Yeah.
Yeah.
Yeah, there's numerous approaches. So what we would call a hybrid approach is where the data is coming from the real field and we're getting certain quality data from there, and then other data, what we call synthetic data, could come from some sort of model or simulation because that data is very expensive or hard to obtain. So yeah, no, it's numerous ways of ensuring we get the data, but also the right data, and it's collected in the right place that could affect, say, reliability or how we should be maintaining the physical asset in the future. So understanding where to get the data in our objects can also be very important as well.
I see we have
Yeah, I do want to point out there's a few questions come in the Q&A, and there's two questions in the chat.
okay. So Chris, can you see the question there? I think the first one, let me read it to you, Chris. You can probably answer that. Using ML for design optimization, specifically for the complicated interconnect, sounds really interesting to me. Is there a place you recommend to learn about this? Well, I guess Chris, I guess this, yeah.
Yeah, I would look here really with regards to these interconnects. It's understanding what drives potential failures, these interconnects. So, how can we model that? So that's what's going to generate the data that we'll be looking at with regards interconnects. But it's actually modeling that effectively. There is quite a lot of literature out there on modeling interconnects and why these failures may be occurring. The whole area of, if you can imagine in the future, having these tests, so thermal cycling, HAST, all being monitored with machine learning algorithms, where you could say, well, I'm seeing something a little unusual here. You don't need to now continue this test because the knowledge we have in these machine learning algorithms is telling us this test will not pass. So after 1 week of testing, you don't need to test for another 3 months. You can now finish here and try another way, because today we just carry on the test and it may fail quite late, which is very expensive and time consuming.
All right. So the next one in the Q&A, apart from packaging, what kind of tools are available currently to utilize AI in process integration? Yeah, because now the process is more complex than ever before. What kind of tools that one can utilize to optimize process flow and reduce number of operations? Quite a lot, I guess, right? Chris, I think the slide I showed, right, the TSM for the 3D Alliance, sure, you can call that packaging slash integration, right? All the major EDA companies are in that alliance because they have to provide the tools, not only to design. I'm sure there, for instance, you heard, yeah, Siemens, for instance, what company not only have a footprint in packaging more and more, but also they're really in terms of manufacturing optimization, right? They have also digital twin and those things in other manufacturing arena as well. So that's where they're trying to leverage their expertise in those other manufacturing process. Yeah, trying to.
Yeah, yeah. And I think it's worth, in that context, Ben, is just to highlight what's happening here at Arizona State University in helping the community optimize these processes. I mean, we are installing, it's based on fan-out wafer level packaging, but we are installing here a complete line at 300 millimeter scales. So there's a lot of things you could do on each of those pieces of equipment in understanding the physics taking place, gathering data on that to support some of these machine learning algorithms of those processes and hence optimization. So having access to that type of infrastructure, I think, is going to be very useful for the community as we go forward.
Yeah, I think now there's 3 more questions in the chat. The first one, what are the biggest challenges you see in accelerating use of ML, AI techniques you presented? How can industry, government, academic collaborate more effectively? Chris, I guess this the Smart USA Institute, right?
Yeah, the initiatives such as Smart USA, which is now up and running. I would advise anyone to go and look at the website. So they've had a first solicitation, and they will be having more going forward. On SRC website and Smart USA website, there is the MAPT roadmap going forward. But I think through initiatives like that, and of course we have the CHIPS initiative here in the US, and in Europe there is the CHIPS initiative there. It's funding like that could support universities working with industry going forward. And we do have a fair amount of investment here at ASU that's supporting, as I mentioned earlier, this whole advanced packaging line at industry scale with 300 millimeter wafer technologies being installed to support prototyping and research, but in particular to bridge the gap from the lab to the fab. Yeah, no, and these are the ways universities and industry can work in packaging, but also in the use of these advanced algorithms, AI and machine learning, to support the industry, optimize our processes, really get much more effective in the design and architecture of advanced packaging for AI as we go forward. And as I mentioned earlier, to help train the workforce.
Yeah, thanks, Chris. So the next question actually interesting. Yeah, so this is actually from a faculty at ASU, Bahar Memarin, I guess, right? She's asking, or she, well, I don't know, was wondering, in the context of AI comes to solve a multi-constraint problem, electrical, mechanical, thermal, etc., for physical and conceptual layers, independently or hybrid. And what are the implication of each? Yeah, I think quickly, I guess that's also one of the challenges that Chris we are facing, right? So I'm doing a group doing a lot of electrical related simulation and design, but you are a lot of focus on the mechanical, right? It is the need to really consider multi-physics altogether. The whole system is need to consider all these physical aspects.
Yeah, it's a multi-objective optimization problem. There is an area of looking also looking at embedding. I talked a lot about generating lots of data, and then you search the data to build your digital twin or neural network. But there's also research taking place where you actually embed the partial differential equations, boundary conditions in the neural network itself. Yeah, in the context of multi-physics, which this question is asking, yeah, it's lots of data or trying to capture the physics in the neural network itself, which is what's known as physics-informed neural networks. And then undertaking what is essentially a multi-objective optimization problem. Because in industry today, you have electrical engineers, they look at signal integrity, they look at EMI, I got it right, there's the package. Goes to the thermal engineer, they look at it and go, this is terrible for thermal. So now we go around this iteration. Where we're moving towards is much more co-simulation, multi-physics, and multi-objective optimization.
Okay. Yeah, I think Nikki will probably almost at the end, right? I guess you have a few more slides to show. I guess.
Yes. And hand over to Brittany.
Wonderful. Well, thank you so much, Professor Yu, Professor Bailey. This has been such an informative discussion, and appreciate everyone adding their questions into the chat and the Q&A. Before we close out today, wanted to just take a moment, share about an upcoming program. We're excited to launch this on September 1st, and it does actually feature Professor Yu and Professor Bailey. For anyone joining from industry, this is a great opportunity to engage your colleagues, whether they're HR, program or project management, marketing and communications, or even public policy, right? To build their foundational knowledge for the semiconductor industry context. So this course, it's not designed for engineers who are working in the semiconductor industry, right? But thinking about expanding the knowledge of the ecosystem across to our colleagues. This is a 6-week program. It launches September 1st. It includes live, online, and on-demand content. And we'll talk through key processes, companies engaging in the supply chain, everything from semiconductor design, manufacturing, and packaging. We'll go through some global trends, investments, as well as some of the CHIPS Act implications and some driving factors that led to Arizona's thriving ecosystem for semiconductors. So invite you to share this with your colleagues if you have folks who you think might be interested. We do have a QR code here and are offering a 20% discount from the price on it. And we'll send this information out in our follow-up email as well. But please do consider it and consider sharing this. Lastly, you'll receive a follow-up email, and it will also include the QR code right here for joining our LinkedIn group. This is a great way to stay connected with us. We'll be having more of these sessions in the future. So please, follow the QR, get connected, and we'll make sure that we keep you posted on any of our next events coming up. But thank you again, everyone, for joining, and Professor Yu, Professor Bailey, really appreciate your time.
Thank you. Thank you, Brini. Thank Nikki. Yeah, thanks everyone.
Have a good rest of your day.
Okay.
Thank you.
Bye-bye, everyone.